Before we begin with a few more examples overriding the equations of a normal line, I want to talk about the equations of the importance, of writing our three-dimensional surface by adding an extra variable p, or whatever variable you want to use. The reason we have to do that is very simple. I want to find the equation of the line, the normal line, off the surface. Now, according to my rule for calculus, this is going to be the gradient. The gradient gives us the direction in the greatest ascent. In other words, it's going to be perpendicular to that surface. So why can't we just use the gradient of f, del f? Why do we have to add another variable? Well, the reason for that is simple. If this is 3-dimension, anything off that surface is basically like a fourth dimension. You can kind of think like as a fourth dimension. If I want to find the quickest direction off a plane, let's say we'd look at the x, y plane. Well, what's the quickest direction off that plane? Straight up. I'm adding a third dimension to this. So if I'm in a 3-dimensional figure, in order to get off the surface, if I want to get off the surface of a 3-dimensional plane, we need a fourth dimension. Not like time or anything like that, but you can kind of see the relationship between a 2-dimensional getting off that plane and off the surface, why you need to add that other dimension. We need another dimension. And to do that, it's very simple to do. If I have my function z equals f of x, y, to get my other dimension, I bring the z over. I would get 0 equals my function f of x, y minus z. And then I can just write this as my other equation. So now, instead of a 3-dimensional plane, surface right here, now we're adding a fourth dimension. And that's going to equal f of x, y, z. Well, I guess I should just say minus z. There we go. Never worked when I wanted to do. There we go. Minus z. And that is why we have to add this extra dimension there, because we want to literally be off this 3-dimensional surface, and the only way we can do that is to add another dimension. So let's take a look at another example up here, number 3. And it says we want to find the set of symmetric equations for the normal line. So we want this perpendicular and off this surface right here at our given point. We want to be off this surface. So the first thing I'm going to do, since I want it normal to that surface, is I have to add my extra dimension. So if I can say that x, y, z minus 12 equals 0, I can now write this as another dimension. I'm adding another dimension to this, and that's going to become equal to x, y, z minus 12. So to write the equation of our symmetric lines, we are going to need our gradient, del p of x, y, z. Be careful. Be careful of the variables here. The derivative with respect to x is just yz. The derivative with respect to y is xz. And the derivative with respect to z is xy. Plugging in our point, 2, negative 3, we're going to get 6, negative 4, got ahead of myself, negative 6, negative 4. And remember, this is going to give us the direction of our normal line. And we're already given a point, 2, negative 2, negative 3. So now we can write our symmetric line right here. To write the equation of our line, it's going to become x minus 2 over 6 equal to y plus 2 over negative 6 equal to z plus 3 over negative 4. And there is our line right there. Right. So let's go and take a look at the last one here, because this is just kind of the same thing. If you need help, our new dimension will be f of x, p of x, y, z would equal x squared minus y squared plus 1 minus z. So you can remember this is going to be z, right? And to find our gradient of x, y, z, we would get 2x negative 2y minus 1. At the point 1, 1, 1, that becomes 2, negative 1. And then I can write my line, my symmetric line, x minus 1 over 2 equal to y plus 2 over 1 equal to z minus 1. Whoops, I keep switching those around for some reason. There we go. Let me fix that. That should be y minus 1 over negative 2, z minus 1 over negative 1. There we go. All right, don't be like me and switch them around. All right, find the set of symmetric equations. Now let's take a look here. Oh, this is an interesting one. Okay, so we got x squared plus 2y squared plus 2z squared equals 20. Again, we want to write this in our new form. We have to add that extra dimension. This is a 3-dimension, but I want to be off the surface, right? So let's see what happens here. We're going to write our function, and that's going to become x squared plus 2y squared plus 2z squared minus 20. So my gradient vector, we got to find that. That becomes 2x, 4y, 4z. At the point 0, 1, 3, we're going to get 0, 4, and 12. Our point, 0, 1, and 3. And when I write my line, be very careful. Notice, my point is, my direction vector here is 0. So what does that tell me? X is never changing. This says that there's no change in x. We've seen this before. It's been a while. This is the one we're going to say just x equals 0, such that, basically, right? So, and then I correct the rest. Y minus 1 over 4 equals z minus 3 over 12. Remember what this is saying. This is a line. This is a line such that, it's saying that, such that all x's equal 0. Don't do this. Don't do x minus 0 over 0. That would be wrong. We just said, since there's no change in x, we can just say x is always going to be equal to 0. I hope you enjoy these videos. I'll see you guys later. Bye-bye.